So, all right, sorry for the delay. Okay, title of my talk is compressing variational base from neural data compression to video prediction. All right, so I'll keep this very brief. I assume you all know pretty well about Bayesian inference, but this is what my talk will start about. I will talk about variational inference as one way of doing scalable Bayesian inference in a fairly efficient way. I'll probably keep this relatively short. And then I will talk about something that I assume a few of you have already encountered before in your daily lives, namely to actually use tricks of the trade from Bayesian inference for practical neural data compression. So we're talking about compressing data of arbitrary type with neural networks, and we really want to kind of outperform existing codecs for image compression and video compression. From there, I will finally talk about connections to time series forecasting, and in particular, we're talking here about very high-dimensional time series, such as video. And you see that there's a little box missing, which I probably won't have time to talk about today, but if I have time to, then I might also talk a little bit about climate science, but that might be difficult. All right, let's get started. So let me briefly introduce kind of why is it important to talk about time and time series. Well, obviously time is a very fundamental aspect of the universe. We observe data in a sequential fashion, and we want to draw conclusions about our data and which state we're currently in. Time series data can be anything from video, audio, observed joint angles of a robot. And we are interested in time series because we want to ultimately understand which state we're in. Right? So imagine you're kind of a robot, and the robot observes acoustic signals, a video signal, and maybe the state of the joint angles. From there, we then want to draw conclusions about the state. And ultimately, we're interested in doing sort of actions, right? Performing actions on the world. Now, as many of you know, there are at least two different ways of how you can model data, right? You can model a temporal signal in a discriminated fashion, or you can also model it in terms of a generative model, right? The subtle difference here is that you have a sequence of latent states, the white nodes here. They progress in time. You have observations that are being fed in, and from there you might be interested in making kind of sort of actions. So this would be the discriminative approach, so kind of treating as a supervised problem. But you could also go the other way around and kind of model the observations conditioned on your latent state, and then use Bayesian inference to infer about the state conditioned on your observations. So the right-hand side is strictly more powerful because, in principle, when your tasks change, right, you might still reuse your dynamics model, and because you hope that the latent representation that you learn is sort of more informative, it might also serve multiple goals. Who of you is familiar with variational inference? Can you raise your hand? Okay, anyone, everyone? So then we're talking about latent variable models here, which we consider probability distributions over data X and latent variables Z that factorize into a joint and prior. We're interested in either the marginal distribution or the posterior distribution, which are both intractable generally to compute because of these high-dimensional integrals that we encounter. And as a tractable way around, we want to do variational inference. And variational inference, we approximate the posterior Q, and in particular, what we do is we make use of an inequality, Jensen's inequality applied to log P of X, and we derive at a lower bound to the log likelihood, which is called the elbow, or the evidence lower bound. And for any Q of Z given X, this is a lower bound. Generally, we want to train our model, so we want to take gradients with respect to log P, but we cannot compute it. So what we do instead is we do gradient descent with respect to theta to the right-hand side, in other words, the elbow, and this is called variational EM, right? So we alternate between a single gradient step over theta and searching for the optimal Q distribution in this functional space of all possible variational distributions. Of course, there can be many different approximations done to this variational posterior. Mean field, it's fully factorized, but oftentimes it's important to model structure as on the right-hand side, right, where you can, for example, model Q order regressively. And in particular, when you care about dynamics, of course, having dependent structure in the latent variables is very important. Okay, so I want to talk about one particular example about the different works that we did on variational inference. And I've picked one example here that is sort of particularly relevant for compression, as we'll see in a moment. So this is joint work with Joe Marino, who actually did an internship at Disney back then, but when I was still working with Disney research. And this is sort of like an ICML paper that came out of it. So what is this called? It's called iterative amortized inference. Okay, so first of all, as you might remember, when we do variational EM, right, we have two nested loops. In the outer loop, we perform a single parameter update step. And in the inner loop, in principle, we have to iteratively search and refine our variational posterior Q. Now, if we do this using gradient descent, which we can do, right, because Q might be a Gaussian distribution in which you would optimize a variance and a mean parameter, then this would result in a generally non-convex optimization problem for any given new input data point X, right? So you see that there's sort of a non-convex optimization landscape, runs of gradient descent, and ultimately we find the optimum. And of course, this is very expensive, right? Because you have to do this optimization in every single gradient step. What we like to do instead is amortized inference, right? In which we predict the optimal U and sigma based on features of X, right? So this would be the Q of T given X. And what amortized inference gives us is like an almost perfect optimum, but not quite, because it's only a guessed solution, right? We have a neural network that's guessing where the minimum of the optimization problem is sitting. And now the question is, if one is fast and imperfect, and the other one is slow but sort of leads to a very clean and optimal solution, is there any middle ground in between? And the answer is yes, and it's called iterative amortized inference, where you do the following. You learn some function f that you not use only once to kind of predict the minimum, but you use it in an iterative fashion, right? So you, for a couple of iterations, you take your previous guesses of your variational parameters, you feed it in, along with the gradient information at this particular point, and you use that to update lambda, right? You run that a couple of times, and it turns out that this gives you a better optimum than just using the inference network in one shot. So you see this here compared to, well, this is kind of primarily a comparison to these kind of fully gradient-based inference procedures, and of course, the iterative amortized inference solution is kind of very, very fast. So only after 5 iterations, you kind of find a near perfect result. Yeah, so this is adopted in quite a different form. Sorry, are you talking to me or are you unmuted? Are you muted? Can you repeat your question? I think this was just some, yeah. All right. Okay. Oh, Heiko has a question. Can you just unmute yourself?
No, I think they raised their hand, but you asked them.
Oh, okay. All right.
Oh yeah, sorry, I raised it that I know variational inference, and then I forgot to put it down again. Sorry about that.
Good to know, Heiko.
All right, I believe you.
So yeah, I know variational inference.
Okay. All right, so then let's talk about something that you don't know, hopefully. And this is now the second part on neural data compression. Is here anyone from Qualcomm by any chance? Probably not. Okay. Yeah, Qualcomm is doing a lot on this space. Let's talk about neural data compression. All right, so the first thing that I would like to talk about is something that you might or may not find surprising or interesting, but basically it's about the fact that you can think of compression as inverse generative modeling. And I want to tell you about that in the next minute or so. So what do we do when we do generative modeling? Well, usually we think that we have some probability distribution over a space of data, right? And we sample from that probability distribution, for example, the space of images. And then a sample from that distribution will then look like a natural image and could be this image of a cat, for example. But what is actually happening under the hood? Well, we probably start from some sort of binary sequence first, right? And we sort of, maybe we could randomly flip the coin and generate the sequence. And then we convert the sequence into a draw from the probability distribution, right? And then we generate the cat image, right? Now, what is compression doing? Data compression, we go exactly the opposite way, right? We start from an image, where we start from a trained model over the space of images. Then we take a new image that we'd like to compress, and we evaluate its probability under the model. And then we use that in order to generate a binary bit string that we use in order to compress the image. As a natural consequence of that, So this would be sort of like some entropy coding step here, where the entropy coder draws on the knowledge of that probability distribution that we've learned. As a logical step, you can actually take any random sequence of zeros and ones, right, where you flip a coin, and decode it, right, using any kind of image compressor, and this should generate an image. And if you do that for JPEG, this is typically what you get, right? You see, it doesn't really look like a real image, of course, but you see, interestingly, a lot of the underlying assumptions of this compression model, how it tries to model the data, and then you see some sort of Fourier components here in the low level, and then on these kind of bigger scales, you see these blocks that are also connected, where they're connected sort of in these lines, right? You see, this is the form of run length encoding plus discrete Fourier transformation that's underlying here. And on the right-hand side, you see another image generated from a neural compressor, like a relatively state-of-the-art model from 2018. And it also doesn't really look like an image. However, if you look, we zoom in, you see a lot of kind of structure that looks somehow much more natural, right? And the fact that this looks much more natural might already give you some idea that, hopefully the neural compressor is actually a better compression model because it sort of models the data more realistically, right? So sort of closer to a real image than you would be on the left-hand side. Yeah, if you're interested in that, there's actually a recent review article that we wrote about everything that I'm going to talk about today. Okay, so how do we do compression with a variational autoencoders? Because these are sort of still nowadays relatively state-of-the-art neural compression model. So we start with a distribution over data. Then we take our variational autoencoder and we kind of encode the image into a latent space using sort of the mean encoding F. And we arrive at a real valued vector. Now, first of all, you might think that you're done because you've achieved dimensionality reduction, but that's of course not the case because you can kind of hide arbitrarily much information in a single real valued number, right? And therefore, without being able to tell how you round or how you can truncate this number, you haven't achieved any compression yet. So therefore, what we do next is we round this vector to an integer vector. And now with this integer vector, we can now actually now losslessly compress this. You could either use an off-the-shelf lossless compressor applied to these vectors, like gzip, but you can actually also do a model-based compression using a density model, which is actually the prior of your variational autoencoder. And using the prior, you can convert this then into a bit string. From the bit string, you can get exactly the same vector back if you want to decompress. And now you push it through your decoder, and hopefully you get an image back that looks highly close to your original image that you started with. Now, just a few years ago, there was this sort of interesting collision between two communities. There was a very applied community doing image processing, Johannes Ballet and others, who developed loss functions for training these kinds of learned compressors. And it turned out that this loss function was exactly the same as a variational autoencoder. And why is this so? Well, first of all, this is the elbow that you would optimize when you train a variational autoencoder. And then you see that if, for example, P is a Gaussian, then log P is a quadratic. So this becomes the distortion. Nothing surprising here, right? The KL between Q and P. Well, if you insert a single sample from Q, this becomes just negative log P. Let's imagine that this is actually a discrete vector. Let's call that P hat. And then this is exactly the rate, the coding costs that you would have to pay when you encode data with your prior model, right? When you encode the discretized vectors. Now, why is it important to use a variational autoencoder? Well, there are 2 points here where this becomes important. First of all, you need a prior, right? Of course. But then also, it turns out that because of the reparameterization trick, you kind of inject noise into this objective during training. And this noise simulates the rounding operation, right? So you inject noise of order 1. This allows you then to safely round this vector to an integer vector. Without noise injection, there could be a lot of information hidden in late decimal places, but by injecting noise of order 1, you can actually safely round to an integer vector, right? So this is actually why there's really variational autoencoders and compression models, and why there's this kind of close connection. Now, we had a paper recently that actually showed that if you know more about variational autoencoders, there are really a bunch of tricks that you can use in order to get better practical compression performance. First of all, there is one inefficiency in the current approach, which is called the amortization gap. The amortization gap refers exactly to this iterative inference idea that I talked about before, namely that if you optimize your elbow using an inference network, this will always be worse than if you're allowed to fine-tune the variational parameters on an individual data point level, right? If you kind of optimize variational parameter for every instance based on gradient descent. Right? So this was exactly what this iterative inference was about. And this is called amortization gap. Now, it turns out when you close this amortization gap by spending a little bit of compute time while encoding an image, you can get a better, more compressed lake representation. There's another inefficiency, namely the so-called discretization gap. And the discretization gap is coming from the fact that when we train our compressive variational autoencoder, we inject noise, right? But when we use it in deployment, we round. Right? And since rounding and injecting noise is not exactly the same thing, the model that you use during testing differs from the model that you optimized. And the difference is called the discretization gap, right? The inefficiency that emerges from that mismatch. Now, it turns out that this can be closed if you directly assume that these variables are discrete, or if you are taking a trained variational autoencoder, and at inference time, you're actually applying a discrete search in the space on the grid of discrete z vectors, right? So that until you find the optimal discrete representation, as opposed to just taking your inference network and rounding the result. So this can be done using a trick called stochastic Gumbel annealing, which is essentially a form of gradient descent with noise that always kind of perturbs your solution that you end up on the grid. And then you kind of do anneal the temperature down, and ultimately this is a form of discrete optimization. Now, it turns out that there's a third inefficiency, which is specifically relevant in hierarchical variational autoencoders. And this is called, this is the so-called marginalization gap. So the state-of-the-art variational autoencoders for compression are actually not simple one stochastic layer variational autoencoders, but they involve two stochastic layers, Z and Y. So what happens actually is that you ultimately you want to encode X to Y, right? But then what you want to do is you want to losslessly compress the discrete version of Y at this level. To this end, you would need a prior P of Y, which you don't really have. You only have a conditional prior times a hyperprior. So what you would really like to do is you would like to marginalize out the hyperprior to learn a really complex distribution over Y, which matches your data well. Because you cannot do that, you actually have to separately estimate Z and Y, which is an inefficiency. And it turns out that there is a technique called bit spec coding that allows you to do lossless compression and closing this amortization costs. And long story short, I don't really have time for that, but here we do a lossy version of that, where we get better to the true marginalization over Z than what you would usually do. Now, how well does this work in practice? So what I'm showing here is a so-called rate savings plot. On the x-axis, you see PSNR as a measure of image quality. So it's related to reconstruction. So high PSNR is high quality, low reconstruction, low distortion, and low PSNR is high distortion. So here we are in the lossy phase. And on the x-axis are the rate savings of different algorithms relative to a certain baseline at different quality levels. Now, what is this baseline? The baseline is the flat curve at 0. So its own rate savings are 0 with respect to itself. And this is the best classical codec BPG. Right? So this is the best non-neural network-based codec. Now see that there are all sorts of curves below it and all sorts of curves above. And there's in particular the brown curve, which is a little bit on par. And this was a few years ago a state-of-the-art neural compression model, a 2-level variational autoencoder. And you see that without any modifications, it's on par with this BPG algorithm. Now, using the tricks that we worked out, you can actually lift the outcome. You can take the trained model and raise its performance by about 20% using these by closing these different inefficiencies that I closing the gaps that I pointed out before. Right? So it really has pretty significant implications, and you can really get 20% better shorter code lengths at the same quality levels across the board. Right? Turns out that you can actually also see that if you take a high resolution image, you zoom in. So this is like some bigger image of a statue or a human playing a statue or whatever. This is what you would get at a certain bit rate, 0.212 bits per pixel. And if you apply this annealing trick at roughly the same bits per pixel rate, you actually see qualitatively better reconstructions. Okay. Yeah. Any questions so far? Yes? Okay, no, good.
All sounds good.
All right. Okay. Yeah, so I'm doing quite a lot of compression research these days. Here are just a couple of more highlights. You can actually think about what's the optimal way of compressing a variational posterior after it has already been learned, using the uncertainty in the sense that you don't want to waste as many bits in uncertain dimensions as you might want to waste on more certain dimensions. This is called variational Bayesian quantization. It turns out that there are these problems called probabilistic circuits, which end up being really useful for lossless compression on certain small-scale image types. And finally, we also did some work sort of on the more technical side or applied side on actually building practical video codecs, which also rely on deep link variable models. And if we have time, we'll talk a little bit more about that. However, rather than talking more about technicalities, I want to talk a little bit more about fundamental aspects of how variational inference can actually not only help neural compression, but how can we do fundamental contributions to information theory. So far, we talked about having about the practical compression model approach, where we have a data set. We learn to map it to a binary representation and learn to reconstruct it. And we use machine learning along the way to serve this goal of developing a practical codec. This time, we want to do something else. We want to study these so-called rate distortion functions. Now, what is a rate distortion function? As I told you earlier, every compression model has a trade-off between rate and distortion, right? We can either choose to have a high-quality reconstruction. So in other words, having a low distortion, we get a very nice looking image out, but then we have to invest a lot of bits to compress it. Or we reduce the bit rate, we make the file size smaller, but then necessarily our distortion goes up, right? So it gets more blurry and the quality decays. And what really distinguishes or characterizes a compression model is how well we do in terms of rate distortion. Ideally, we want to push this curve as far down as possible, but it turns out that there's a fundamental limit. And this fundamental limit is the rate distortion function. Right? The rate distortion function is really a theory, a curve that always exists. It's only a function of your data set and of your distortion measure. And it tells you kind of how much it should be possible to compress your data set up to a certain distortion, and at which point should it become impossible to compress it further. Right? So it has a certain information theoretical definition. It's called as the infimum over encoders Q, Y given X, subject to having a certain minimal distortion. I'll kind of discuss this a little better. And then looking at neutral information. So it's you can already guess those are all high dimensional conditional distributions, and it's very difficult to compute these quantities in general. And what we really would like to do now is to use machine learning in order to estimate the rate distortion function, independent and irrespective of any model or any compression scheme, right? Only a property of the data. Okay. So I think I can skip this a little bit. So this is a typical rate distortion function. You can, I think I already talked about this, right? You can either have a high rate and low distortion, in which the images look good, or you can have high distortion and low rate. And we're interested in sort of estimating this resulting curve on an empirical data set. Okay. All right. So, yes.
So does this depend on the size of the data set? With more data, does that curve move down, or is it always?
In some sense, yes. I guess you can think of it as the entropy being a particular limit of that curve, in the sense that for entropy, it would correspond to the limit of zero distortion, right? And you can think of this as a generalization to entropy. where you have a certain tolerance level, right? You're no longer asking to losslessly compress the data, but you're asking, how compactly can I compress it such that I have a certain minimum distortion or maximum distortion level. Yeah, so I guess if you make it more diverse, then the rate distortion function should move up. Yeah.
So here you're assuming some variational family Q, right? So doesn't your rate here also depend on your choice of variational family?
That's true, but here we're really asking, so by definition, it's defined as an infimum over all possible functions.
Oh, this is over all functions.
Over all functions,
over
all conditional
family.
distribution that exists.
Yeah.
Right. Yeah. Right. Yeah. And so this slide is mainly to say that this is a really difficult object, right? Those are all these definitions, and and in fact we're really faced with a minimization problem over conditional distributions, which is even worse than a minimization problem over functions, which we already cannot solve.
What is rho here?
Rho is our, oh yeah, maybe I should have mentioned that before. Rho is actually our distortion measure. So you can think of this as mean squared error between data points x and the so-called reconstruction y. Right? So y is the decoded data point, so that you get out. So we're, so this is the mean squared error between x and y in the simplest case.
But how in this setting is the decoder defined in terms of the encoder? Right,
yes.
like what mathematical symbol represents the decoder in this set of equations?
Oh yeah, sorry. This is actually a slightly more general setup where we don't necessarily actually operate in a latent space at all. We only assume we have the data source x and we have a so-called set of reconstruction points y, which you could think of a subset of x, or discrete versions of x, or a grid, right? So you can formulate this also in the presence of a latent space, but you don't need the concept of a latent space in the most general formulation.
Okay, great.
Yeah. Right. And so what does the rate distortion, assuming we could compute it, what does it tell us? Well, you give me a pair of rate distortion and another pair of rate distortion, and I tell you which one of them could be feasible and which one is fundamentally possible to achieve. Yeah?
But you can't compute RD, right?
Exactly.
So,
we still can compute RD. But we would really like to have it, right? So that's okay. So what would we do? So we cannot compute RFD. We have no analytic form, and it's very hard. And information theorists have worked on this for a long time. They've mainly looked at Gaussian distributions to compress this, or low-dimensional problems. And they have one algorithm, which is called Lahut-Arimoto algorithm, that scales exponentially in the dimension, and which you can actually only work with up to 4 dimensions. Right? So it's really, really difficult. Fundamentally hard to think to compute. So what do we do instead? Well, instead of when we don't compute it, maybe we can actually sandwich it from both sides. Right? This would be already useful, because an upper bound would tell us what should be in principle possible to achieve. Right? And if our practical compression algorithm lies above it, we know, oh yeah, there's a sizable amount of gains that we can still expect. On the other hand, a lower bound is also highly useful, because if we are already pretty close to the blue curve, we don't know it, and the gap is small, then we know, well, probably doesn't, we're pretty close to what's not possible anymore, right? So maybe it doesn't make sense to invest any more resources in improving compression methods. Yeah, so we're the first work that we're aware of to try to approximate this purely based on samples using machine learning methods. And it turns out there are 2 contributions. There's an upper bound and a lower bound. So the upper bound, maybe you're not so surprised about it, but it turns out that every beta variational autoencoder, any beta variational autoencoder, gives you an upper bound on the rate distortion function. Right? At first you might think, well, that's trivial, right? I know that variational autoencoders are basically compression methods, right? And any practical compression method is actually already giving me an upper bound. But note that not every variational autoencoder is immediately a practical codec, right? There are many. I told you that there are many differences still to the neural compression method, and so it's still interesting that VAEs are always bounding the model-independent rate distortion function, right? And now, if you find better and better architectures, and you can play around arbitrarily with latent dimensions, then all the resulting rate distortion functions will be envelopes of the upper bound. Okay. Now, maybe more interestingly, you can also derive lower bounds, and this is actually fairly complicated, and you see that this slide is super superficial. But basically, what you can do is you can compute a Lagrangian dual to the rate, the way I formulated the rate distortion function, which leads to a maximization over functions, and with a nasty constraint. And it turns out that now, if I restrict functions to a certain class of neural networks, then clearly the maximum over the restricted class of function is smaller than the overall global maximum, and so that results in a lower bound.
What is GFX?
Yeah, I mean, those have no natural interpretations. It's some function of the data. Yeah, so you're trying to kind of maximize over any g's and any lambdas such that.
Oh,
you know,
sorry.
There's
Yeah,
no,
sorry,
you know,
you're
it's just like
maximizing
it's the object that you
And
maximize.
again, this is any function.
Any function. Yeah. It's kind of kind of nasty. And then there are also these really nasty constraints. So this here is saying that the exponential of negative rho, which is actually something like a likelihood, right? Because log rho was the log likelihood, can be interpreted like rho is a distortion, so that can be interpreted as a beta VAD's likelihood divided by that g has to be integrated over all data space, has to be smaller or equal to 1, right? So this is constrained on g, right? You can imagine that this is a little weird.
Let me know once we're interrupting too much. But so when you have a beta VAE, right? Normally in a standard VAE, you have
Yes.
a log likelihood term and you have this beta term.
Yes.
But if, let's say, your log likelihood is a Gaussian, you can also just scale the sigma of the Gaussian. And so you can trade kind of the strength of the reconstruction loss and the KL loss
Yes.
arbitrarily, right?
Yes.
In the discrete section setting, this must be a little different. Is that true? Like does this parameter lambda now have, which is, I guess, a bit like your beta constant in the beta VAE, right? Like,
Yeah.
does that now have more of a fundamental meaning, or is it
Yeah, it
equally
has-
undefined because you could always redefine your log likelihood?
It has a slightly different meaning because this is, again, without reference to any particular model. I mean, this is completely independent on VAEs.
Sure.
It turns out that this is sort of like the offset of the linearized lower bound to the rate distortion function where it intersects the y-axis.
I see.
But
I see. Okay.
anyways, yeah.
Thanks.
Yeah.
Yeah.
All right. Yeah, so if you're interested in that, I refer to the paper. You know, we have a lot of things to talk about today, but I'm really excited about it. And let's see how well these bounds actually work in practice, right? So it turns out that we can parameterize both the upper bound and the lower bound by neural networks, right? And this gives kind of sandwich bounds to the rate distortion function. Now, I don't want to set expectations so high, so let me tell you first that the upper bound is highly scalable and the lower bound is not so scalable. It turns out that because of this nasty optimization constraint, it's really, really difficult to optimize. But you will be surprised how far we can actually still push it up, right? And I told you that this baseline only scales to 4 dimensions, right? So let's start with 16 dimensions then, right? So here we have a physics data set of some particle collisions. You know, 2 particles collide and decay into 2 other particles. And so we have 16 momenta, right? 16 4-dimensional momenta. And now you can actually cross-collate all of them and see that there's a lot of interesting structure between these different dimensions of these vectors. Right? And now let's imagine that we want to compress this data set with or we want to estimate that data set's rate distortion function. And we did that, and you can actually derive these up and compute the upper and lower bounds. And this gives you, the red curve here, the light red for the upper bound, the dashed red for the lower bound. And now we know that the true rate distortion function is somewhere here in this region. Right? And now to understand if this is a trivial result or not, we can actually also try to compress the data as good as we can, and we get the blue curve. So this is the best existing compression method. We see that there's a tiny gap still, right? We could potentially improve that by a little bit at least, and this is what theory told us. Right? But now we can really quantify how far we are away from this rate distortion function. Now, if we go to 2 dimensions, we project the data into 2 dimensions using a PCA. We can visualize it. It looks like this. So you see there's a lot of structure still. But now in 2 dimensions, we actually have a baseline, this Arimoto algorithm from the 70s, right? And this gives us the actual rate distortion function. We see it's indeed in the middle, right? And so nothing went wrong. Everything is expected, right? So this is a sanity check that our bounds are sort of not trivial or that they're not off by any numerical issues. Now let's go to a little bit higher. We can also generate a speech data set or look at a speech data set of spoken digits 1 to 9, right? So you see that this is already a pretty simple data set, but still it's actual speech. And you could look at these histograms, and they actually are images, if you will, right? Now you can compress these. And again, you can compute upper and lower bounds. We know that the RD function is somewhere in the middle. And again, we are still a little bit off. We can't actually compress this perfectly, but we should be pretty close to it. Right? So that's what our analysis gets at. And again, we can do a sanity check by going down to 2 dimensions. Now, you might wonder, is this sort of completely trivial? Can we only go to 33 dimensions? And it turns out what really matters is not so much the ambient space dimension, but the intrinsic dimension of the data. And to show this, we actually generated a lot of images using a GAN, but we modified the GAN in such a way that it's effectively having exactly 4-dimensional latent space, right? We took a trained GAN, we set most of the Z vectors dimensions to 0, and we only sampled in a 4-dimensional subspace. And if you do that, then you actually get kind of images of the same dog in different poses, turns out. Right? So this is a real artificially generated high-resolution image.
Oh, so this is the 0 dog? This is the dog you get that you set almost everything to
I think
0?
this is the 0 dog, yeah.
Right, nice.
This is a famous, have you heard about it before?
I think you could call it the 0
Yeah,
dog.
the 0 dog, yeah. So the question is, can we compress this data set, and can we estimate that data set's rate distortion function? And the answer is yes. So here it is, right? So this is actually pretty surprising. I mean, given the fundamental hardness, right, of estimating RD functions for real-world images, when we constrain the data set's intrinsic dimension, we can actually compute it. And also, what's even more interesting is, if you now compare this to the real neural compression algorithms, they're kind of way off, right? At least this one here. Right? So all of this here should be harvestable. And in fact, this here is a very modern compression method, right? You see that there's still a little bit gap left over, right? So that's kind of makes us very optimistic that there's still room for research to improve compression methods. And remember that this is actually artificial data. This is not even real data, right? Yeah, so it's kind of really useful in practice. If you look at the upper bounds only, so like you can also look at rate against quality. It's a slightly different plot, but almost the same. So high rate means high quality. And what we did is essentially all this, our results essentially indicate that the shaded blue area here should be harvestable in principle by compression methods, whereas all of these here are different existing compression methods, right? So we're not quite there yet, and we can actually improve more. We should be able to get more performance out. And again, this curve could be in principle way up here, right? This is only a bound, right? So it could be much further up. Okay. Any questions so far before we move on? Yes.
So if you want to get the upper bound tighter,
yes,
you need. Are you using the standard upper bound of the mutual information, which is that if you take the KL between the variation distribution and the prior, you have the mutual information plus the KL between the inference marginal and the prior?
I think I think that's basically it. The difference mainly is that we define the data-dependent rate distortion function not in terms of a likelihood model, but in terms of a distortion metric. That's sort of the main difference.
Sure. Yeah. And so is the name of the game in getting it tighter to get your encoder to encode to data that looks more like the prior?
That could be one thing, yeah. I mean, basically, getting variational bounds tighter is the thing, right? So the tighter your variational bounds are, the better. But the thing is, the nice thing is it doesn't have to be a compressive variational autoencoder. So for example, one thing we're still planning to do is to use Stein variational gradient descent, which has only an implicit prior, right? And doesn't really, yeah, and that might get us even better estimates. Yeah. All right. So let's talk about the second part, which is about time series modeling. Yeah, that's the question here.
So I have a question.
Yeah.
Let's consider the scenario in the signal you graph by the noise.
Yes.
So previously we developed the denoising autoencoder is able to filter the noise and recover the signal. Right?
Yes.
So when we apply the latent error model for the compressed representation, so can the term latent error distribution reflect the noise or reflect the kind of uncertainty from the input?
Sorry, I'm not sure if I understood your question correctly. So shall we maybe discuss this offline? So you're saying that, or yeah, okay.
Yeah.
Or maybe you kind of try it again. Yeah.
When the signal is grabbed by the
Yes.
noise, so can the probabilistic debate reflect this kind of method?
You mean now in a learned compression approach? I mean, yeah. I mean, I guess it is somewhere. It is reflected in the latent variable, right? But yeah, but it's not necessarily a good thing. Yeah. All right. Cool. All right. Let's talk a little bit about what I also promised to talk about, namely about time series modeling, and then let me later on tell you why this is actually connected. And let me quickly check how much time I have. Yeah, I guess. Okay, give me 5 minutes to keep it a little shorter. Yeah, time series models can be factorized over time using the chain rule of probability, and in general, it can have a very complicated likelihood model and a very complicated prior. This is the most general formula, right? And then, of course, you all know hidden Markov models, which are a very simplified version of that most general factorized model. However, hidden Markov models are, of course, not capable of generating kind of temporally coherent sequences because they're basically first order Markov. And also, they're not really flexible if you use with simple distributions. However, what you can do, and this was one of the first things that was trying to make this more nonlinear, was, for example, the model the P of zt given zt minus 1 in terms of a neural network, putting out a Gaussian distribution with a certain mean and a certain variance. And so this enters feeds linearities in there. You can also condition on the entire history of what's been already generated. And with tricks like these, you can now suddenly model, of course, dynamics of high-dimensional video and things like that, right? So it's a lot of research on that. And some of the most important papers are listed here. So it started, to my knowledge, in 2014. And then variational RNN is a pretty popular kind of stochastic RNN in this space for time series forecasting. And there are all sorts of other developments built on top of that, which we don't really have time to cover. I also worked on this in 2018. We have this paper called Disentangled Sequential Autoencoder, where we tried to disentangle content from dynamics. So we had a late variable model with structure and time plus a global late variable f that conditions on every frame. And then the hope would be that we could sort of disentangle motion from content. And for simple data sets, we were successful at this point. And this was actually my beginning to think about video compression because, when we are being able to predict next frames, should be in principle very useful when we also compress video as a sequential data set. Now, all of these sequential variational autoencoders have huge problems currently. So here's a comparison from this clockwork variational autoencoder paper. And basically what they are is they lack long-term coherence. So you see that these walking characters tend to vanish at times. They're not really scale up to high resolution content. They're always kind of fairly restricted to small scale toyish data. And also what people don't do properly oftentimes is to evaluate them quantitatively. They mainly look at perceptual qualities when they try to generate video. Here's the idea that we had. Given the correspondence of compression models as generative models, right? Couldn't we just take a video compression model, generate a random bit string, decode that bit string, and generate a video this way, right? And of course, we wouldn't use like a simple or kind of a classical neural code, a classical codec, because that would not really look like a video. But what about if you use one of these more modern neural codecs that have been developed? Right? And here's really quickly how these methods work. You imagine you have a scene from a movie. I don't know what kind of action movie that is, but there's like some high rises. There's some explosion in the foreground happening here, right? Probably Spider-Man or I don't know what. And the first thing that you do is you try to make a prediction for the next frame, right? That's what your video compression model does. It tries to predict the next frame, and it's pretty good at the background. But you see that it's fairly blurry and uncertain in the foreground, right? So because there are way too many details in this explosion. To still nevertheless memorize the video well, you have to look at the residual between the prediction and the ground truth image. This might look like an image like this, and you compress it separately as an image. And because it's a sparse image, you can actually compress it very cheaply. During reconstruction, you can just additively add them together, and this actually gives you the next frame. Yes. Yes.
Sorry, really short question. Here, the residual is really gray. So does the predictive model more or less get the colors right, or is that not always true?
That's not always true. It doesn't have to be, I guess, right? I guess, yeah. I guess if it's all gray, yeah, it's a good question. Yeah, I mean, I guess if it's uniformly gray, it might still be cheap to compress. All right. So the question is then, can you run this model as a generative model? And long story short, no, because video compression models are not really built for generation, right? The residual model is not conditioned on the history. It's just compressing this as an image. And so the errors will accumulate and the image will not look good, right? And it's also not really coherent on a more macroscopic scale. So what we did is we looked at diffusion models. Just who has seen diffusion models before? Can you raise your hand? Everyone? Okay, then you know what a diffusion model is. And we use these diffusion models conditionally as our residual compressors. So here's a frame sequence. We use this frame sequence to predict the next frame deterministically. Yeah. And then we condition a diffusion model on also the entire history. And this diffusion model will then generate a residual, which is sparse. And then additively, we add them together. And this generates the next frame. Here's the corresponding graphical model where we encode the history. And we use that to condition our diffusion model to generating the next frame. So important thing here is we don't attempt to directly model the next frame. We really model the residual. And that turns out to be better. Now, looking quickly at results. So here is a relatively high resolution video data set showing the scene of a car from the perspective of a car. Here's the car coming from the side, as you can see here, a little bus, right? And the car is moving to the front. So this is ground truth. And now this is a residual diffusion model. It's actually pretty sharp and turns out also quantitatively reliable, as I'll show you next. The VAE models tend to become blurry over time, and the GAN models invent all sorts of structure, and they're typically temporally also not coherent. Right? So this is kind of pretty good progress in terms of being able to predict high resolution content. What I'm really excited about is to be able to predict fluid dynamics, for example, using these models, in particular also in climate applications. So it turns out they're more reliable than GANs, maybe unsurprisingly. You can also evaluate them quantitatively by looking at a quantity called continuously ranked probability score, which is looking at the model's cumulative distribution and the empirical cumulative distribution at the next time step and comparing them. And inverse CRPS higher is good. And then you see, if you look at future frames, you have always this exponential decay, meaning that it's harder and harder to predict future frames, but the diffusion model is typically always on top and the GAN models are at the very bottom. All right, I think I'm basically off my time. I'll not talk about climate. I'll go to the last slide. And I'd like to thank my collaborators. Yeah, so I talked about many things. I talked about nonlinear hidden Markov models for video forecasting. I talked about variational inference, in particular iterative inference. And I talked about a lot about neural data compression today. And for video forecasting, we really want to get better long-term generation, multimodal prediction, and high-resolution scaling. And I'd like to thank a lot of my collaborators, particularly Ivo Yang, who did a lot of the compression work, and Robert Bandler, who's now at Tübingen, a former postdoc of mine. So with that, thank you very much. Any questions? Yes.
So one of the messages I got from the talk, thanks for the talk, by the way,
sure.
is by improving inference, we improve the compression, and also studying these like rate-distortion curves. But it seems like our quality metric is just fundamentally misaligned.
Which metric?
So the quality metric for the log likelihood or the PSNR.
Yeah.
It could be these images or audio which have, according to this metric, high distortion.
Yeah.
But really, to a human, it doesn't look. It looks the same. Or a very simple example for audio would be, our reconstruction is bad, but it's in frequencies, in which humans don't care about. It's or something like this.
Right.
And I'm wondering, so one maybe avenue is like, okay, can we improve the alignment of that? And there's some amount we can gain by the inference over techniques. There's probably a different amount we can gain by improving how much our metrics
Yeah.
actually reflects what that's human sense.
Yeah.
I'm interested
Yeah.
in your sense of the relative magnitude of the improvements there.
Yeah, absolutely. Great questions and comments. Yeah, indeed. I mean, in fact, not only improving the inference can matter, also improving the modeling can, of course, help. And you're perfectly right that one weakness of the current evaluation is that we always look at this relatively narrow metric of rate and distortion. And distortion is mean squared error in particular. So it turns out that if you do compression with, for example, diffusion models, you oftentimes get visually much more appealing results, but because they're not optimized for distortion, you get kind of qualitatively worse results, right? And there's actually a huge space of evaluating compression models also. Like if you look at our paper, there's a lot of literature on how you could potentially improve the evaluation of models, looking at perceptual qualities, their perception distortion metrics. You can do user studies, of course.
Do you think that seriously comes up in evaluation? Because wouldn't ideally we train
yes,
models?
you can actually, you can also directly train the model for perceptual metrics. That's also been done at times. Yeah, totally. Yeah. Right.
Short question, sorry. I was just curious if I might misremember your RT curves that you show, but does the bound get looser at higher in your experience, does the bounds get looser at higher rates, or was it in general?
Yeah, let me remember. Yeah, I think there was some pattern. Yes. Yeah. Well, here it's not so clear. Yeah, here you see always this trend. Yeah, from what I remember is the low distortion tends to be more difficult. Yeah, you're right. It's intuitively clear, I guess, right? Because here the data set gets simpler to model in some sense, right? It's very difficult. So what we see, for example, if you would try this here instead of like 100 dimensions, you would go to 1,000,000 dimensions. The upper bound would still look similar, but the lower bound would be extremely flat, right? And so, so that's very hard to estimate. Yeah.
Maybe a little. I have a question if you have time. So you do the variational inference is completely deterministic. So because if you're doing compression and you have some form of stochastic algorithm that gives you better inference, then of course you have to compress all the stochastic steps. Right?
If you want to do lossless reconstruction,
yes. But the variational inference doesn't give you that problem, I guess, right? It's not optimization.
That's true. Yeah, that's true. I mean, we use it actually in lossy compression for the most part, in which case it was actually fine, because you would then ultimately only compress the result of that inference. But there are definitely algorithms where you have to think about determinism. So, for example, what I briefly talked about in terms of closing the marginalization gap at bit square coding, that's where you really have to think a lot about these issues. Yeah.
All right.
All right.
Well, thank you again for a fantastic
talk. Thank you.